Hey, everybody. It's Wednesday, April 28th. And as you can see here in the aim today, our goal for today's video is all about reviewing the free response question that was assigned yesterday. If you remember, this was the question that was assigned under the title on AP Classroom, AP Physics FRQ Review, Day 9. Now, I like this question. Part of what I like about it is it's a pretty good mix of conceptual simple harmonic motion stuff with some calculations and some experimental designs. But really what I like about this question is there are a lot of ways that you can approach this. And really, ultimately, that's what I like about this question is you can come at this question, as we're going to show here, from a number of different ways and still get the same answers. And so let's get into it. Here, as I'm sure you remember, problem says the student hangs a 0.125 kilogram object on a spring and sets it into oscillation and obtains the data for the position and velocity of the object as a function of time, as shown in the graphs below. And you can see there the position graph, measured in meters, of course, and then the velocity versus time graph, of course, measured in meters per second. Now, something to notice about this, I think, is definitely that the velocity graph has these like weird spikes in it. That's perfectly okay. They like to do this stuff on the AP test. They think it's so cool when they give you like real world data for you to work with. It's fine. You don't really have to go too nuts about it. If there's a part of the graph that you think is going to be interesting, but it has like a little spiky or wavy part on it, then just go to the next one, because usually they'll show other parts of the graph, that look like you would expect it to, which is just like a nice smooth curve. So they give us the position and the velocity data. And the first part of the question asks to sketch the potential energy of the object spring Earth system as a function of time. And it says to explicitly label any intercepts, asymptotes, maxima, minima with numerical values as appropriate. And then part B asks for you to do the same thing, but with the acceleration. And so what I hoped you recognized is based on the graphs that were given here, we have a good amount of information, but we don't have enough to be able to draw those graphs right away. And there are a lot of ways that you could think about this question, as I mentioned, but the way I see it, the way I thought of it when I first looked at this question is I'm going to need some information to be able to make these calculations. Specifically, I'm going to need the spring constant. And so I figured the first move here that we should do, and I'm going to show this a couple of ways, the first move should be to determine the spring constant. Now, hopefully you realized when you were looking at this position as a function of time graph that something's a little weird about it. And that's that it's not centered at the origin. It's centered up here about a value that's not even labeled. If you look very carefully at this graph, you realize the line starts halfway between 0.4 and 0.6, so that's at 0.5, and then it goes up to 1. And so that means here this graph is centered on 0.75 meters. And so that was the first thing to pay attention to, at least I think, because the amplitude, remember, is the distance from the equilibrium position. And if you went from 0.5 to 1 and said the amplitude was a half a meter, that is wrong. The equilibrium position is at 0.75 meters. And so that means the amplitude here is just going to be 0.25 meters. That, of course, depending on the way you do it, is going to be an interesting number, if not immediately, then a little further down the line. Part of what you should also realize is that these graphs, and this is the way I first thought of it at least, and we'll talk about some alternate methods here in a second, part of what you should realize about these graphs is they enable you to determine the period. The period, whichever way you see it from either graph, if we say the period is the amount of time it takes for the thing to complete one cycle, if we're taking it for the position graph, it starts at the negative most displacement, goes up, down, and back again by 1 second. Notice here, even if you don't want to do it from there because you think it's weird to start at like the negative peak, if you will, you can go positive peak to peak. It goes from 0.5 to 1.5. So there, the period is 1 second. Or you can go from 0 to 0, like here, which looks to be at about 0.75 seconds, and then to the next one here at 1.75 seconds. And of course, if you're going from 0.75 to 1.75, the period is going to be 1.0 seconds. Now, of course, it's usually the way we look at it when we see these position graphs to determine the period from the position graph, but you can also determine the period from the velocity graph. It starts at 0 here, goes up, comes down, goes back again. This is your traditional sine curve here, and it's 1 second. Of course, if you go peak to peak, It's not as straightforward because it doesn't start on a nice spot here, but this is 1.25 seconds. Then over here, we have halfway between 2 and 2.5, so that'd be 2.25 seconds. No matter which way you cut it, the period of the oscillation is 1.0 seconds. And the way I see it, because there are so many equations for simple harmonic motion where the spring constant is an important number, if we want to draw that potential energy graph and we want to draw that acceleration graph, a good number for us to have is going to be the spring constant. And I think I've mentioned this pretty clearly by now, but there are a lot of ways that you can go ahead and determine this. And so we'll show two of them now. The first thing that should be noted here is the mass of the object is given in the problem as 0.125 kilograms. And of course, we just determined the period was 1 second. So in our list of knowns here, we'll write the mass is 0.125 kilograms. We'll write the period is 1.0 seconds. Now, the period is an important thing to determine in this experiment, obviously, because like the main point about simple harmonic motion is that it is periodic, but also because there's a nice equation in the reference table which relates the period of a spring to the spring constant. Specifically, it's that the period of the spring is equal to 2 pi times the square root of m over k. And so, as we've discussed so far here, this equation is a little annoying to solve for k. The first thing we have to do is we have to move the 2 pi over to the other side. And so we have the period over 2 pi times the square root of m over k. Then, of course, we're going to have to square everything. So we have the period squared over 4 pi squared, and that's going to be equal to m over k. And then, of course, when we solve that thing for k, we're going to do that by moving that up and over, the 4 pi squared up and over. So that's going to give us 4 pi squared m. And then, of course, we're going to have to divide by the square of the period. But there it is, our equation for the spring constant. Now we can go ahead and plug in. We have 4 pi squared, and then we have to multiply by the mass here, which remember the mass is 0.125 kilograms. And we're going to go ahead and divide that by the period, which easily for this one is just 1 second. So 1 squared is going to be 1. And when you do that math, making sure you have all those numbers plugged into your calculator correctly here, 4 pi squared times 0.125 kilograms divided, of course, by 1 ends up giving you 4.9 newtons per meter. Now, of course, that's just one way of determining the spring constant. And so what I want to do now, just very quickly, is show an alternate method. If this is the way that you solve for the spring constant over here on the left, and you feel like you don't need to watch this next part because you're good and you figured it out, I would recommend that you watch it anyway, because it's always good to be able to figure out multiple ways of doing these problems, because if they restrict the information a little bit, you might find yourself in a tough spot. Going back to that graph that we were looking at before, it's very important for everybody to realize, yeah, we can look at this graph and determine the amplitude of the position versus time graph, but we can also look at this graph and determine the amplitude of the velocity versus time graph, or in other words, the maximum velocity, or at least the magnitude of the maximum velocity. And if you look very carefully at this graph here, let me see if I can erase some of this ink so I can uncover it a little bit. I hope what everybody recognized when looking at least a clear section of the graph here, that the amplitude of the velocity versus time graph, or the maximum velocity, is clearly over 1.5 meters per second. We'll go ahead and call that 1.6 meters per second. Now, obviously, that's an estimation. And that's the nature of experimental determinations, is that we look at the graph, we have to make an estimate. Even though it is a fancy piece of experimental equipment that would produce this graph here, it's important to realize, nonetheless, estimating the peak is going to be part of the deal. And so from this graph here, we can see that the maximum speed is 1.6 meters per second, or the magnitude of the maximum velocity is 1.6 meters per second. Now, of course, the question is, well, why is that important? Well, coupled with the amplitude being 0.25 meters, we can use that to determine the spring constant if we know the mass, of course, 0.125 kilograms. And the way we could do that is basically just by saying the maximum kinetic energy, well, that's going to be equal to the maximum spring potential energy. Now, I like this part too, because we have to draw a potential energy graph in a second. And so this way is actually a perfectly good way to go about it. When we do that, we end up equating 1/2 mv max squared and 1/2 Ka squared, of course, because the potential energy is maximized when the amplitude, or when the position is maximized, or in other words, when the thing is at its amplitude. When we do that, the halves cancel. And so it's important to realize one thing here. Obviously, we can use this equation straight away to just solve for the spring constant as K equals mv max squared over A squared. Now, some of you who did this might have started from this equation, V max equals K over M times A. That works too. That's totally fine. Having said that, it is good to know where this Vmax equation comes from, because in a situation like this, if you know how to derive the Vmax equation, it's actually easier to solve for K, setting it up this way than to have it be set up in this way, because you end up getting Vmax over A equals the square root of K over M, then you got to square both sides. It ends up being kind of annoying. This is a nice, clean way to do it. And so notice here, if we take these numbers and we plug them in, 0.125 kilograms times our Vmax, which we said was 1.6 meters per second squared, and we divide it by the amplitude of the oscillation squared, 0.25 meters squared, we end up getting a spring constant of about 5.12 newtons per meter. Now, I know some of you looking at that might think, well, wait a second, that's not the same answer as the other one. Well, that's the nature of experimental equipment. Sometimes your answers are not going to be totally close, but it should be noted that 5.1 and 4.9 are not meaningfully different in an experiment like this. They are close enough, and we will continue to show that as we go through the rest of these calculations. It's important for everybody to understand that regardless of the way that you approach this, getting the spring constant now enables us to draw both graphs. And that's really, really important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on to part B here, moving on to part A here. We haven't done that yet. We just found the spring constant. Part A is asking us to sketch the potential energy of the object, spring, or its system as a function of time. And of course, we've got to label any intercepts, asymptotes, maxima, minima with numerical values as appropriate. Of course, they're only telling you like intercepts, asymptotes, maxima, minima, or whatever, because they don't want to give away the answer. They're just basically saying label the important stuff. And what I hope everybody realizes is one piece of the important stuff is going to be figuring out the maximum potential energy here in this problem. And so that's what we've got to do first. Now, of course, we found out that the spring constant is 4.9 newtons per meter. I guess I'll write here or 5.1 newtons per meter. We'll show it both ways. And we have the amplitude is a quarter of a meter, 0.25 meters. And we're looking for the maximum spring potential energy. And so we could do this two ways. Of course, 1/2 Ka squared is going to be the only equation that will allow us to find that, at least directly. And so we have the spring potential, I guess I should write max here, is equal to 1/2 Ka squared. So that's going to be 1/2 4.9 newtons per meter. And then we're going to say that's times 0.25 meters squared. And when you do that math, making sure you have all those numbers plugged into the equation correctly, you get 0.15 joules. Now, I'm just going to go through and show these other calculations very quickly. So the first thing we can say is, well, what if you did the spring constant calculation the other way and you got the spring constant as 5.1? Well, is that a problem? No. As I mentioned, these are not meaningfully different as far as the answer is concerned. So instead of doing 1/2 of 4.9 times the amplitude squared, we're going to do 1/2 times 5.1 newtons per meter squared times 0.25 meters, whole thing squared. And when you end up doing that math here, you get the spring potential energy ends up being 0.16 joules. Again, I know a lot of you are probably looking at that and thinking, well, that's not the same number. But it's very important to remember in experimental physics, close enough is good enough. And those numbers are close enough. Now, I'm sure some of you might be looking at this, though, and thinking, well, wait a second. I didn't do this way at all. There is actually a very clever workaround here that at least lets you to start off this graph here at the top, graph A, without finding the spring constant. And basically, that would involve you in just recognizing, well, this velocity reaches a maximum value, which means the kinetic energy reaches a maximum value. And even though the potential energy is 0 when the kinetic energy is at a maximum value, energy is conserved. And so if I just find that maximum kinetic energy, I can find that elastic potential energy. And that would be exactly right. Notice here, we can also just find Kmax using the information that we could have really pretty readily obtained from the graph. And I think this is a really clever way of thinking about it too. So if you thought the spring constant is going to be the way to go and had to do that, that's a perfectly reasonable way to do it as well. I kind of wanted to go through all of these things anyway, and so this is why I introduced it in the order I did. But either way, we could take 1/2 of 0.125 kilograms times 1.6 meters per second squared. That's our V max. And we square it. And then when you do that math, plugging it into your calculator correctly, you get 0.16 joules. So either way, no matter which of these three methods you used, how you found the spring constant, how you calculated the energy, your answer is somewhere around 0.15 or 0.16. So this is the way we should approach it. We're going to write 0 here because 0 is going to be an important number. We're going to write 0.1 joules and then 0.2 joules. And we're going to have to put the peak of our potential energy graph somewhere in the middle there. Now, I hope everybody realized if you're trying to draw the potential energy graph without looking at the position graph, you're crazy. Because the position really ultimately determines what the potential energy graph is going to look like. The first thing we should say is that wherever the position is 0, well, that's where the potential energy is going to be 0. And notice, because these axes are all set up the same, that's going to be directly in between the dotted lines. So 1/4 of a second, 0.75, 1.25, 1.75, and so on. And so that's at least the first marking here we can make. We're going to say the potential energy here is going to be 0 here, 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 and here. Now, some of you might have noticed by now, I haven't labeled anything on the negative side of the graph. It's very important for everybody to realize here. Energy is a scalar, and so it's never going to have a negative value. Now, of course, the reason why they give you space above and below the x-axis is because part of this was really testing if you know that. Now, if you're thinking, well, wait a second, go back to that position versus time graph. Some of the positions are negative or are below the equilibrium point. How can you possibly argue that the energy isn't negative? Well, I would say, first of all, energy is a scalar, so it's just not. But the second thing you could say is, well, either way, the position in the potential energy equation is squared. And so as a result, it doesn't matter. Even if you square a negative number, it's going to end up being positive. These numbers are never going to be negative. And so now that we have our values, really all the values we need, we should just actually probably go back to the position graph one more time and just make note of when this thing is going to be maximized. And I hope everybody realizes at the amplitudes, whether they're positive or negative, this thing is going to be maximized. And so basically at 0, 1/2, 1, 1.5, and 2, and really we could go 2.5 also, the potential energy is going to be maximized because the potential energy is maximized at the amplitudes. And so we'll say that maybe that's going to be like 0.15, 0.16 right there. And we'll try to put that at the same height for all of them. Of course, if you're actually taking this with a paper and pencil, you can use a ruler for this part, make that real easy. And so we need to have our graph pass these points. And I think that's an important thing to realize. And of course, I hope everybody realizes because the position oscillates sinusoidally, so does the potential energy. So the graph is just going to look like this. And of course, it's not so easy to draw. It's not a drawing competition. It's really hard to draw with the digital pen, so I apologize for how garbage this drawing is here. But it should look a little something like that. Of course, sinusoidal. Now, I hope everybody's in agreement that that drawing is not good, but that is going to be enough to earn you the points. But that is what your drawing should look like. There's a lot of information contained on the slide, and I'm going to switch off it here in a second. So take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, let's take a quick look here at the scoring guide then for part A. If we take a look at the scoring guide for part A, notice here the scoring guide for part A says 0 potential energy can be defined at any point. For convenience, define it to be the equilibrium point of the hanging object. Now, I said this in a video that a very small number of you watched. It was a video about the vertical spring, clearing up some of the misconceptions about it. You don't need to talk about gravitational potential energy for a vertically hanging spring if you consider the 0 point to be the equilibrium point of the hanging object. Because above that, technically, the gravitational potential energy would be positive. Below it, the gravitational potential energy would be negative. Remember, gravitational potential energy is weird because it actually can be negative, but we can avoid that altogether if we just recognize here that we don't ever have to mess with gravitational potential energy for a vertically hanging spring if we make the equilibrium point the 0 potential energy line. Now, some of you might be thinking, wait a second, what the hell are you talking about gravitational potential energy for? Notice the question did say the object spring Earth system. So that was an important thing to pay attention to. Now, I want to be very clear about one thing. The solution to this problem, as shown in the scoring guide, in my opinion, looks just really weird. They're showing basically the maximum kinetic energy minus whatever the kinetic energy could be at any point, basically 1/2 the mass times the velocity as a function of time squared. Then they're writing an equation for the function of the velocity and then showing this whole calculation. It's really important to just focus in on this part. What they're using there is just a calculation of the maximum kinetic energy. And they're saying the amplitude of that graph would be 0.16 joules. And so that's how they're calculating the energy. We already talked about how you can calculate the energy in a bunch of different ways. This way of doing it, I think, is the most idiotic way of thinking of it, at least of writing all of this stuff out. Just calculate the max energy. It's a more straightforward approach. There's no reason to write the function. Anyway, you get 1 point for a graph with a reasonable sine squared shape. Notice this is a sine squared graph because it doesn't have any of these negative values. 1 point for having the maxima of the graph at the labeled times. And then for having maxima and minima, there's no point in drawing the minimum energy as anything other than 0, but they allowed for that. For having maxima and minima with a potential energy difference of about 0.16. So if you had a sine squared shape, you had the zeros in between the dotted lines and the amplitudes at the dotted lines and, of course, at the 0, then you got full credit for this one, of course, considering if you put the height as 0.16 joules. Take a second to pause this video here and take a good look at the scoring guide, making sure you understand all aspects of it. And when you hit play, we'll move on. And that brings us to part B. Part B of this question here asked us to basically do the same thing we just did, but for the acceleration. Now, this part, I think, is not so hard, or at the very least, not so involved. The first thing you have to recognize is we have to label maxima and minima. And so we're going to have to calculate the value of the maximum acceleration. Now, some of you might remember this equation. It's A max equals K A over M. But of course, if you forgot that, knowing how to derive it is good. Of course, we need our spring constant here. And I'm just going to say for the moment that that's 4.9 newtons per meter. Our amplitude here is 1/4 of a meter. And our mass is 0.125 kilograms. Now we're looking for the acceleration A max. And so the first thing you do, remember, when you try to find this equation is you say, well, the only force acting here is the spring force. Remember, if we are considering the equilibrium position to be the place where all the heights equal 0, we don't have to mess with gravity. And so here, we can just say that Ka, where the force is maximized, produces M times A max, where the acceleration will be maximized. And of course, then we can get it by doing K, 4.9 newtons per meter, the spring constant. Solving for A max, of course, you would get Ka over M. I skipped a step there. Sorry about that. Times the amplitude here, which is 0.25 meters. And then we're going to go ahead and divide that by the mass, 0.125 kilograms. And when you do that math here, you get 9.8 meters per second squared. Of course, that's just a coincidence. Now, just to be clear, if you use the spring constant as 5.12 newtons per meter on this part, you end up getting 5.12 times 0.25 divided by 0.125, and that ends up giving you 10.24. And so I think the basic idea here is this thing is supposed to be in the ballpark of about 10. Now notice, for the scoring guide for the last part, it just said, for having maxima and minima with a potential energy difference of about 0.16, they were not going too nuts about the values for this question. All right, so we know the maximum here is supposed to be 10. And so for this, obviously, we can label positive 10 meters per second squared and negative 10 meters per second squared, because we know we're going to need both here for this kind of problem, because the acceleration can be both positive and negative. And now we need to think very carefully about the way this graph is supposed to look. I think it's really important for everybody to remember. You have to look at this graph properly, in my view, put this horizontal line here showing the equilibrium position. Because one of the most important things we said about acceleration versus time graphs is that the acceleration is always going to have the opposite sign of the position. So I think we should take this bit by bit. Let's just do the first half a second. The position starts negative, then goes to 0, then goes positive. Negative, 0, positive. Negative, 0, positive. The acceleration's got to be opposite. So instead of being negative, 0, positive, it's got to be positive, 0, negative. So we have positive, 0, and then negative. Now we can go along for the rest of this here, and let's just do the next second, because hopefully you realize this is a pattern. If we go to the next half a second here, now we have this thing at its peak positive position, so that'd be the peak negative acceleration, and then it goes to 0 and then negative. So this is just going to go 0 and then positive. And then notice here we could just fill in the rest. It's going to be a cosine. Now, for all of you calculus nerds, you might remember, now that's a joke, of course, you might remember, now I sketched that a little off there, we'll have to back this up. You might remember that, well, the velocity graph is a sine, and so the derivative of a sine is a cosine. That's the idea. Now, I actually decided not to cut this part of the video out just now, because I think it is important, maybe once you recognize it as a pattern and you're bad at drawing like me, to fill this stuff in, because having the dots there to trace might make it a little easier for you to prevent yourself from making a mistake, because drawing these functions is hard to figure out exactly where you're going to put the curves. And so I think, it is a little easier with paper and pencil, in my view, but having the dots to sort of connect the dots here on this one, I think is a bit of a smarter approach, in my opinion. Now I'm going to move on to the next slide here. So there's a lot on this slide. Take a second to pause this video here and write this down. And when you hit play, we'll move on. All right, moving on to the scoring guide here. I accidentally showed it a second ago. Notice here the graph looks just like we had it, except better. And it says here, for a graph that is either a sine or a cosine curve. Pretty good. Even if you totally messed up the maximum and minimum locations they would have given you here, if it's just sinusoidal in any way, a point. They gave you 1 point for a graph that has an appropriate phase relationship to the given position and velocity graphs. What does that mean? Basically, that means it's a cosine, positive. Because what you notice if you stack all these graphs up like in a vertical line, they're all just basically shifted versions of one another, right? The cosine is just a shifted sign. I hope you understand what I mean by that. It's basically just shifted by a fraction of the cycle, basically where instead of starting on the 0, it starts at the amplitude, right? And so what they mean by this second point here is that wherever the position is negative, the acceleration is positive, and vice versa. And so notice here, this ends on a negative. If your graph ended on a negative because you had it drawn the right way with the whole thing, then you're good. It had to be a cosine looking like this. Now, of course, they end up showing the calculation here for the acceleration, but the last point was for an amplitude of approximately 10 meters per second squared. They ended up showing the amplitude being just under 10 because they ended up leaving the spring constant as a half pi squared, so they didn't round, and that ended up giving them an acceleration of 9.87 meters per second squared. And that's the scoring guide for Part B. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. And now we're moving on to part C, the experimental design portion of the question. Now, I do think it should be noted, this question is from the 2014 practice exam. That was the first practice exam that ever existed for this course. I think you've been able to get a sense by now, they have changed the format of an experimental design question. They do not make it so open-ended like this. They have that chart where you put the materials that you're going to use to make the measurements and so on. You guys have seen this before. I hope you know what I'm talking about. But this was one of the old versions of the problem. It's a little open-ended, but since we've done a few experimental design questions by now, I figured it was fine. This question here says, next, the student is given a rubber band and asked to determine whether the relationship between the restoring force exerted by the rubber band and the amount it is stretched is the same as that of an ideal spring. Well, what is the relationship between the restoring force exerted by the rubber band and the amount it is stretched? If we knew that for a spring, that would make this a heck of a lot easier. And the point is, you should. But part C is asking us, what is an experimental procedure the kid could use to collect the necessary data, including all of the equipment? So notice they're not giving us that chart. We have to mention it throughout. You should know that the relationship between the force the restoring force and the amount it is stretched is Hooke's law, Fs equals Kx. And this equation, notice it says whether the relationship between the force and the stretch is the same. The relationship between the force and the stretch is that they're directly proportional. So basically, we need to be able to come up with an experiment to show whether the force is directly proportional to the stretch for a rubber band. Notice a perfectly good way of doing that would be a graph. And I think what is really crucial about understanding the basics to these concepts is that if you graph the force versus the displacement, well, then the slope is K. And so basically, you can think of this as an experiment where you're measuring the spring constant and trying to determine if it's constant. Because if the graph is linear here, it'll show a constant spring constant, which shows that the spring force is directly proportional to X, which is what they're asking us to do. Here's my answer. I wrote, according to the equation for the restoring force exerted by the spring, Hooke's law, the force exerted by the spring is directly proportional to the distance from the equilibrium position of the spring. I should say of the spring. In order to determine if this relationship holds true for a rubber band, we need to measure the force exerted on a rubber band and the distance the rubber band stretches from its equilibrium position. In order to determine the force acting on the rubber band, we can hang masses from the rubber band in 10-gram increments until they reach equilibrium. So like if you hang a mass on a rubber band, it's going to be flopping around a little bit. You got to let it settle. I wrote, in this instance, the force exerted by the rubber band or on the rubber band by the masses will be equal to their weights, which will, of course, be determined by their mass, Fg equals mg. In order to determine the mass of the objects, we can place them on a triple beam balance 3 times and average the mass readings together. Now, of course, masses have their mass printed on them, but as you would know if you were in the lab, an often neglected high school physics laboratory has 10-gram weights that do not have a mass of 10 grams. They get chipped and dinged and decay a little bit because they're usually made of radioactive metal. And so they end up being like 9.9 or whatever, something like that. And so the idea is you actually want to measure them and not just take the number at face value. Now, of course, the averaging the mass readings together thing sort of covers us on that, avoiding experimental uncertainty business. You've seen that in previous scoring cards. In order to measure the distance from the equilibrium position of the rubber band, we can measure the original length of the rubber band with a ruler and meter stick, measure the length reached by the rubber band when the weight settles, or when it reaches equilibrium, and then subtract those values to determine the distance from the equilibrium position. We can repeat these length measurements multiple times for each mass and average the results together. Starting with 10 grams, we can repeat the whole procedure for masses of 10, 20, 30, 40, and 50 grams. Take a second to pause this video here and look over this explanation. Notice the level of detail. Notice the mention of the equipment used. Notice some of the steps to uncover or to sort of get around experimental uncertainty. And when you hit play, we'll take a look at the scoring guide. All right, moving on to the scoring guide here, they gave 1 point for a reasonable experimental setup that would allow useful measurements. They gave 1 point for indicating all measurements needed and no extraneous ones. And they gave 1 point for evidence that multiple trials are performed. Now, again, you've seen scoring guides written since this question was written. This question is now 7 years old. It is important to realize that they have sort of changed the way they've written these scoring guides for labs, but this overall kind of covers the bases. Notice here they just said hook the rubber band over a horizontal rod and measure its length, hang an object of known mass from it and measure the new length, repeat for a number of different objects. That's a pretty bare bones explanation. They said hang an object of known mass, which I thought was cheating because there's not really such a thing because these masses of these things are not constant. But, you know, for this year, that was good enough. Now, as you've seen since in experimental design questions, they usually don't ask so much up front like they did in this question by asking you to draw the graphs. But I do think it is an important thing to point out that the detail here is going to be important on these modern experimental design questions. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the last part. All right, part D is really where they want you to get into analysis mode. So it says here, how should the student analyze the data to determine whether the relationship between the restoring force exerted by the rubber band and the amount it is stretched is the same as that of an ideal spring? What evidence from the analysis would be used to make the determination? Now, there are a lot of ways that you could talk about this, I think, that would satisfy what they say as like appropriate and reasonable. But I think making the graph is so crucial for these experimental design questions, and that's the reason why I've talked about that for the whole year. So what I wrote should not be a surprise to any of you. Since Hooke's law tells us that the relationship between the spring's restoring force and displacement from the equilibrium position is that they're directly proportional, we must determine if the same is true for the rubber band. We can do this by determining, quote, if the spring constant is constant. For the spring, the fact that the spring constant is constant tells us that the slope of the line on a graph of force versus displacement would be constant. If we graph the force versus displacement from the equilibrium position and draw the line at best fit, we can determine if the force is directly proportional to the distance from the equilibrium position. This, of course, is for the rubber band. If the graph is linear, or if the slope of the line at best fit is constant, then that would show us the restoring force is directly proportional to the distance from the equilibrium position. It's all about that graph in this question, in my view. Take a second to pause this video here and write that down, adding any parts of this that may be mixing from your own explanation. And when you hit play, we'll move on to the scoring guide. All right, taking a look at the scoring guide here for part D, it says 1 point for an appropriate analysis that would check for a linear relationship between force and rubber band stretch. Now, I don't think you had to talk about a graph here, but I think that would have been smart. 1 point for indicating an appropriate characteristic from the analysis that signifies a linear relationship, like a constant slope. And 1 point for indicating that a linear graph means the rubber band exhibits force is proportional to displacement, like an ideal spring. So their example was plot the rubber band stretch as a function of the mass of the object. I thought that was kind of bogus. Fs versus x is like a classic thing, so you could have forced it, so to speak, by multiplying m and g. And then it says here, a linear graph would show that the stretch and the force exerted on the rubber band, i.e. the weight of the object, are directly proportional as they are for a spring. And that's it. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, everybody, that is it for today. I hope this question served as a good little review for you for simple harmonic motion, considering that we have a test coming up this week, the last unit test of the year. Please, 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 if you have any questions about the way the scoring guide is written, about the way you did the work, please let me know in comments or email. And that's it. Have a good one, everybody.